Ionic bonds, the transfer of electrons from metals to nonmetals. As we go through today's lesson, we're going to focus on the following three essential questions. What holds atoms together in a chemical bond? How do positive and negative ions form? And how does ion formation relate to electron configuration? Let's first start by defining what is a chemical bond. In the last unit, we learned that elements in the same group have similar properties because they have the same number of valence electrons. So on the periodic table, that looks something like this. We divided these up into groups. So we said this is group 1, this is group 2, and all of the elements in group 1 have one valence electron, and because of that, they have similar properties. Valence electrons are the first thing to collide when two atoms meet. So look in our pictures down here, we see the electrons in red. When these two atoms come in and collide, the valence electrons are the first two things to meet. Valence electrons are involved in the formation of chemical bonds. So let's write down our definition. A chemical bond is nothing more than a force of attraction that holds two atoms together. There's no actual physical line or stick. It's just a force of attraction that holds two atoms together. There are two options for chemical bonds. The first is the attraction between a positive nucleus of one atom and the negative electron of another. So here I can see that the electrons are being shared. So I'm going to put that here. They are being shared. So this positive nucleus is attracted to its neighbor's electrons, and this positive nucleus is attracted to its neighbor's electrons, and because of that, they're both holding on to each other's electrons, and they're essentially stuck together. So this causes a force of attraction that keeps the atoms together. Here we have the attraction between a positive ion, we call this a cation, and a negative ion or an anion. So here, this atom has lost electrons, and because it's lost electrons, it's now positively charged. So this whole thing is positive. Over here, this substance has gained electrons, so the whole thing is negatively charged. I'll put gain here. So I have an attractive force between a positive ion and a negative ion that makes these two atoms stick together. These are two different types of bonds. Here, they're sharing, and here, electrons have been transferred, but nonetheless, they are attracted to one another because of opposite charges. Let's also review how to draw Lewis dot diagrams. We're going to look at the top of each group number, and we're going to use that group number to identify number of valence electrons and number of dots that go around our atom. Hydrogen is in group 1, so we will draw one valence electron. Magnesium, if we pull up our periodic table, magnesium is a group 2 alkaline earth metal. I'm going to draw two dots to represent its two valence electrons. 1, 2. Boron is in group 3, so we will draw 3. 1, 2, 3. And notice I'm just going around the atom itself. Carbon, or the symbol that represents the atom. Carbon is in group 4, 4 valence electrons. Nitrogen is in group 5, so I'm going to put one electron in each of these four corners. After I've used up all four corners, then I double up my number of electrons. This nitrogen, because it's in group 5, needs one more valence electron, so I've drawn it there. Oxygen is in group 6, 1, 2, 3, 4, 5, 6. Fluorine is in group 7, 1, 2, 3, 4, 5, 6, 7, and neon is in group 8, 1, 2, 3, 4, 5, 6, 7, and 8. Ionization energy was energy needed to remove an electron. Electron affinity was the attraction for electrons. So the question is, what is the trend for each of these on the periodic table? We should have seen that as we move to the right, the pull of the nucleus increases, and ionization energy and electron affinity also increase. As we move down a group, electron affinity and ionization energy decrease. So then the question is, if I compare the nuclear strength of a group 1 metal to that of a group 7 nonmetal, what might occur if they are fighting over an electron? So if a group 1 metal has an electron, so let's say this little bunny here represents the electron, and this is my group 1 metal, and here is my group 7 nonmetal. If I compare their nuclear pull or effective nuclear charge, a group 1 metal or a group 7 metal is much stronger than a group 1 metal. So if they are essentially fighting over this electron, who's going to get it? Well, group 7s have a stronger pull on electrons, so they will completely remove the electron from a group 1 metal. Recall that a stable electron arrangement is low in energy and involves a complete octet. So that means an atom will have 8 valence electrons in their outermost energy level. And atoms can do that by gaining, losing, or sharing electrons. How are positive ions formed? Positive ions are called cations. A way to remember that is that the T in cation looks like a positive charge. Atoms can lose one or more valence electrons in order to form a noble gas configuration. These are typically our metals that lose one or more valence electrons. So let's compare the electron configuration of neon to that of sodium. What do you notice? For neon, I see it has 2 electrons in the first energy level, and it has 2 electrons in 2s and 6 electrons in 2p. If I add up the electrons in the s and p, the outermost energy level, I see that it has 8 valence electrons. Now when I look at sodium, I see that it has 2 in energy level 1, that it has 8 in energy level number 2, and in energy level 3 it has 1 valence electron. So the difference is that sodium has an additional electron. It has 1 in energy level number 3 that is preventing it from having a stable electron configuration. By losing the electron in 3s1, sodium now has the electron configuration of neon. But don't be misled. Sodium hasn't become neon like we saw in nuclear chemistry, and that's because its number of valence electrons does not change the identity of an atom. So what I'm going to see here as the electrons are transferred, if this sodium loses that electron in energy level 3, sublevel S, the only thing that remains is what matches that of sodium. So the way the electrons are arranged match the configuration of sodium or of neon. But it doesn't mean that sodium has become neon. It just has its electrons arranged in the same way that neon does. How do negative ions form? Negative ions are called anions. This is where atoms gain one or more electrons to attain a stable outer electron configuration. And these are typically our non-metals that are gaining electrons. Let's compare the electron configuration of chlorine. It's a group 7 halogen to that of argon, which is a noble gas. So if I look at my electron configurations, here's chlorine. Energy level 1 has 2 valence electrons, or just 2 electrons. They wouldn't be valence because they're not in the outermost shell. Energy level 2 has 2 in the s and 6 in the p for a grand total of 8 valence electrons. And then in energy level number 3, I see that there are 2 electrons in the s sublevel and there are 5 electrons in the p sublevel, which means there are 7 total valence electrons. To have a complete octet, chlorine needs to have 8 valence electrons. So it looks like it needs to gain 1 additional electron to fulfill the octet rule. If I look at argon, argon's configuration is nearly identical to that of chlorine. The only difference is this. Argon has 6 electrons in the p sublevel. So if I look at energy level 3 with 2 electrons in the s and 6 electrons in the p, it has 8 valence electrons and an octet. Just like chlorine, all of group 7A atoms have the tendency to gain 1 valence electron to become stable. So this chlorine will gain 1 additional electron to match the arrangement of electrons of argon. Now, it's not becoming argon, it's just matching the electron arrangement of argon. How many electrons must group 5A gain for a stable electron configuration? Well, the goal is to get to 8. So 5A elements are going to gain 3 electrons to have a noble gas configuration, and group 6A elements are going to gain 2 electrons to have a complete octet or a noble gas configuration. How does an ionic bond form? It's important that you know that an ionic bond forms between a metal and a nonmetal. The image to the left shows a reaction between sodium metal and chlorine gas. What is happening in this reaction? So I have 2 sodium atoms reacting with 1 chlorine gas molecule to form 2 sodium chloride formula units. The metal, that's sodium, loses an electron to form a cation, so it becomes positively charged, while the nonmetal gains the electron from the cation to become an anion. It becomes negatively charged. The 2 ions form an ionic compound. What is an ionic bond? The electrostatic force, the attractive force, that holds oppositely charged particles together in an ionic compound. So my metal becomes positively charged, the nonmetal becomes negatively charged, and we've always heard of the rule that opposites attract. So this is an electrostatic attraction between oppositely charged particles that holds them together. Most ionic compounds are binary ionic compounds. This means that they're made up of only 2 different atoms. They're always between a metal and a nonmetal. Let's take a closer look at how sodium and chlorine combine to make sodium chloride. So I'm going to look at these Lewis diagrams and the electron configurations to help me see how this ionic compound is formed. Sodium is a group 1 alkali metal and has 1 valence electron. Chlorine is a halogen and has 7 valence electrons. In order to complete its octet, chlorine needs to gain 1 additional electron. And because chlorine's nucleus is stronger than that of sodium, it's strong enough to completely remove that valence electron. This arrow is showing the electron moving from sodium to chlorine. As a result, sodium becomes positively charged. Sodium starts out with 11 protons and 11 electrons. But with the removal of 1 electron, it now only has 10. I can see that the number of positives outnumber the number of negatives, so it has a positive 1 charge. Chlorine, on the other hand, has gained an additional electron. It now has 8 valence electrons, and it started with 17 protons and 17 electrons. That's its atomic number. By gaining an additional electron, I can see that the number of negatives outnumber the number of positives. There is a lot of energy released. We would call that an exothermic reaction when sodium and chlorine combine to make sodium chloride. If I were to look at the electron configurations, I see that there is 1 electron sitting in the 3s orbital, energy level 3 sublevel s. We're going to take that electron and we're going to move it over here to chlorine. Chlorine has this little empty spot here, and we're going to fill it in with that electron. Now these arrows simply represent electrons. 1 electron moving up and the other electron moving down. We put them in opposite directions because electrons are so repulsive that even if they're in the same energy level, they would have opposite spins. I can only put 2 electrons in each box. So what I see here is once this electron for sodium has been removed, now I see that energy level 2 for sodium is completely filled. It has 2 electrons in 2s, and it has 6 electrons in 2p, so energy level number 2 for sodium has 8 valence electrons. Now for chlorine, because we added that additional electron to fill that little gap right there, now I'm looking at chlorine. It's energy level number 3. 3s has 2 electrons, 3p has 6 electrons, and when I add those together, it has 8 valence electrons. Let's take a look at how calcium and fluorine form an ionic compound. Calcium is a group 2 alkaline earth metal. That means it has an oxidation number of plus 2. Fluorine is a halogen. That means that it has 7 valence electrons and will gain 1 additional electron to have a complete octet, which gives it an oxidation number of -1. So we want to know what is the combination of these ions that's going to result in a formula for this compound. A formula is the symbols for each of the elements in a bond with subscripts that tell me how many I need of each one. Calcium has to lose 2 electrons to obtain a stable electron configuration, and fluorine has to gain 1 electron to attain the stable configuration. The number of electrons lost and gained must be equal. So therefore, 2 fluorine atoms are needed to accept the 2 electrons lost from the calcium atom. So what I see here, for every 1 calcium atom that has a positive 2 charge, I need 2 fluorine atoms with that -1 charge for the overall charge for calcium fluoride to be 0. So that means for every 1 calcium, I need 2 fluorine ions to complete my formula here. I want to show you in a diagram what this looks like. So calcium would have 2 valence electrons. I'm just going to draw them on opposite sides. Fluorine has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. So if I were to show the transfer of electrons, calcium loses its electrons and fluorine gains them. Fluorine can only accept 1 more electron to fulfill its octet. 1, 2, 3, 4, 5, 6, 7, 8. But this calcium, it still has that 1 valence electron. So this doesn't do my calcium any good if it can only lose 1 electron. It has to lose 1 more. So I'm going to draw another fluorine on this side with 7 valence electrons. There's 4, 5, 6, 7. And now I'm going to show this electron moving to this fluorine. And now my calcium has lost 2 valence electrons. My fluorines have each gained 1 electron, and the transfer is equal. Calcium loses 2, fluorine gains 1, so I need 2 fluorine atoms to complete the transfer. So my formula would be for every 1 calcium, I need 2 fluorine atoms, and that's why you see the number 2 here. Let's conclude today's lesson by going over a few properties of ionic compounds. The chemical bonds on a compound determine many of its properties. Ionic bonds, for example, make crystals, like the borax ornaments that you made last week. Why do they make crystals? Because ionic bonds aren't just one single bond between one metal and one nonmetal. It's actually millions of them put together. The strong attractions among the positive ions, remember we call those cations, and negative ions result in the formation of a crystal lattice. So here, this is a sodium chloride crystal or table salt. If we were to zoom in and look, this is actually a repeating pattern. Sodium is this little gray guy and it's positively charged. Chlorine is this yellow, kind of that neon yellow-green color, and it is negatively charged. So sodium chloride isn't just one Na and one Cl. It's just a repeating pattern. NaCl, 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 and it goes over and over. So I can really identify there's NaCl, there's NaCl, here's NaCl. So they're all over. I've got this nice repeating pattern. So a crystal lattice is this repeating pattern of positive, negative, over and over and over until I get this 3D structure called a crystal. What can be observed from the structure of a sodium chloride crystal? It's a repeating pattern. What is the ratio of sodium ions to chloride ions in this crystal? For every 1 sodium, there is 1 chlorine in this picture. So the formula for sodium chloride is NaCl. The next physical property of ionic compounds is the ability to conduct electricity. Ionic compounds are great at conducting electricity as long as they are molten. That means that they have been melted from the solid to the liquid state, or they're dissolved in water. What exactly is the ability to conduct electricity? It means that we can introduce electrons to our sample, and the electron should be able to go all the way through and complete a circuit. That's what conducting electricity is. So if I take these ions that are charged particles and they are free to move, that means that they have been molted, they're in the liquid state, or they're dissolved in water like shown in this picture, then I have positive cations that can attract electrons and pull them in. And I also have these negative electrons that are repelled, or negative ions that repel the electrons and can push them through, almost kind of like a ping pong table. We're pushing the electrons through. Can an ionic solid conduct electricity? And the answer is no. I need to have mobile charges in order to conduct electricity. An electrolyte is an ionic compound whose solution conducts an electric current. We talked about that back in the first 6 weeks when we went over physical versus chemical. Just make sure you have that definition there. The strength of conductivity is determined by the number of ions in solution. So the more charged particles I have in solution and the greater the charges on those particles, the better the ability to conduct electricity. The next physical property of ionic compounds is that they have high melting points and high boiling points. Ionic bonds are the strongest of all the bonds that we'll talk about. And that's because there are so many attractive forces. There. They're just all over the place. Because it's not one single bond and it's millions of them, it requires lots and lots of energy to break those attractive forces apart. The next is that ionic bonds are crystals that are hard, rigid, and brittle solids. When an external force is strong enough to overcome those attractive forces, so say we apply a force here. Look at my setup now. I have 2 positives and 2 negatives if we apply a force. So if this happens, if we apply a force, the crystal cracks and breaks apart, and that makes them very brittle. So instead of being able to bend them without breaking, if you apply a force, they will break. And last but not least, ionic bonds are the strongest of all types of bonds. And the lattice energy is the energy required to remove ions from an ionic compound. So if I have this attractive force between sodium and chlorine, it's how much energy does it cost to separate those 2 ions apart. So for Ni and Cl, it costs 769 kilojoules to break apart this attractive force. The greater the lattice energy, that's this number here, the stronger the force of attraction. The lattice energy is directly related to the size of the ions that are bonded together. So remember, distance was one of the factors that we talked about last unit. We said that the smaller the radius, or the closer that positively charged nucleus is to those valence electrons, this distance here, the stronger the attractive force. So the smaller the ions are that are transferring the electrons, the greater this lattice energy will be. Smaller ions produce strong attractions, which leads to greater lattice energies. Electrostatic force of attraction between opposite charges increases as the distance between the charges decreases. So the closer the positive and negative ion are, so I'm looking at this distance here versus, say, this distance here, this says that as the distance between the charges decreases, so here I've got a really short distance, the force of attraction increases. So this would be a stronger attractive force because they're closer than this. Ionic bond formed from the attraction of ions with larger positive or negative charges generally has a greater lattice energy. So the last part of it, let's compare really quick. If I have sodium and chlorine, that's been our example so far, so we'll keep it. Sodium is +1 and chlorine is -1. But if I take something like magnesium chloride, magnesium is +2 and chlorine is -1. So this is ionic bonds that are formed with larger positive. So this is a +2 versus a +1. It will have a greater attractive force for chlorine than this sodium will. So the more positive the charges or the more negative the charges, the greater the lattice energy will be.